Okay, so here we are for AP Physics Accelerated Frame of Reference Problems. I'm going to do selected problems from this assignment. Let's start with problem number 1. What horizontal force must be applied to the cart shown so the blocks remain stationary relative to the cart? We're going to assume all surfaces are frictionless. So this cart, someone is applying this force F, all right, to this cart and shoving it, right? This big cart of mass M. Attached to it is this pulley and these two masses, right, M1 and M2. Now you would think that, this problem got messed up in the diagram. Dang it. Sorry, when I transferred images from Microsoft Word into Google Docs, images, sometimes things get shifted around. Can you see that the string isn't lining up? Dang it. This is supposed to be M2. It is up against the edge of big M. Dang it. So it is up against it here, okay? That's really important for the problem. Sorry about that. Man, it's not going to make much sense without that. Anyway, if this cart was sitting still, you would agree that M2 would fall and slide M1. And since this is frictionless, you're like, oh, this would accelerate down and this would accelerate over, right? Okay. Except because this is accelerating, right? Then it turns out that this is not, in fact, going to descend at all. It will stay like this, all right? And the blocks will remain stationary relative to the cart, all right? How that works and all, we're gonna get into that as we go through the problem, okay? So we wanna know how hard I'd have to shove here in order to make it so that these blocks do not move. This does not descend, right? And then this, then it's gonna move, see, here's the key, at the same acceleration as this cart has, right? They're going to accelerate together. All right, so this won't be moving along. Okay, so that's the idea. All right. So what I'm going to do, like every force problem, I realize that I'm going to get my answer F in terms of the variables given. So these three masses and common universal constants like G, right? Okay, so that's the idea. So what I'm going to do is I'm going to choose systems. Okay, I think that I'm going to go ahead and start by making force diagrams. Let's make big M a system, the cart a system. Let's make M1 a system and M2 a system. I think I'm going to do it like that. I could also do all three together or combinations of them, but I think I'm going to be okay with doing three diagrams, one for M1, one for M2, one for M3. So, I mean, big M. So that is my plan. So here we go. So I'm going to start with a force diagram for big M. I shouldn't do that. Oh, well, too late. Here's force diagram for big M. I should have done it so it's spaced spatially like it is on this page. You know what? Woohoo! Look at me. Burn a piece of paper. All right, here we go. So here we go. Start with M1. So here is M1. All right. Quick. All right. And you say, hey, what forces are going to act on M1? You say ranged forces. There'd be a gravitational force. M1G, right? And then contact, the only thing touching it is big M and the string, right? So big M, you say, yep, they're being pressed together, so there'll be a normal force. I'll draw it right here. Here's a normal force. What am I going to call this? On one, I should have called this M3. Look, watch this. Executive decision, I'm going to call this M3. On 1 by 3, okay? All right. And then you say, hey, are the surfaces trying to slide against each other? Kind of, but everything's frictionless, so I don't have to put a friction on. And the other thing is a rope attached, so it's a string. Is it being stressed? It certainly is. This is yanking on it, right? So we're going to draw in a tension. Okay? All right. That's my force diagram for this. I think we can see right away. Wonk, wonk. This isn't accelerating up and down. Those are going to balance. Okay. Let's do a force diagram for the cart, which I'm going to call M3. All right. I've changed my mind, calling that M3. You say, okay, ranged forces. Well, there'll be a gravitational force. Okay, I'm going to call this M3G. Okay, and then contact forces. What's touching it? Well, there's kind of whatever is applying that force there.
Attention, please. All custodians to the teacher's cafeteria. Attention, please, all custodians to the teacher's cafeteria.
All custodians to the teacher's cafeteria. All right, here we go. Starting off here, there's this, whatever this exterior force is, whatever's shoving on it there, I'm just going to draw that in, big F. That is the force I am attempting to solve for in this problem. Okay, that force that's pushing and accelerating this whole system along. Okay, then contact, what's this touching it? Well, the ground, right? So there's like, going to be this, I don't know, normal force on 3 by, I don't know, the floor. Okay, so N3F, okay? The other thing touching it is M1 is pressing down on this. Just like there was a normal force on 1 by 3, there'll be a normal force on 3 by 1. The other thing touching it is this block. And again, I apologize that that diagram got screwed up there. These are in contact with each other. They definitely are. They have to be. And so they're going to be pressed against each other. So there will be a normal force on 3 by 2. Okay. And then if I do block 2, there's no friction forces, right? And then over here, M3, M2, I mean, you say forces on it, range forces, there's gravitational, M2G. Contact forces, you're like, what's touching it? The rope and M3. M3 is going to be pressing against it. We are accelerating M3, right? So something has to accelerate M2 to the right. That's going to be this normal force here, normal on 2 by 3. And then there's that tension going up, and that is it. Okay, those are my force diagrams, all right? And I know that this looks pretty ugly. You're like, oh my gosh, there's 1, 2, 3, 4, 5 forces on that. That's not so bad. 3 here, 3 here. Okay, so what comes next? You're like, well, of course, we're going to use the most important formula in physics, right? We're going to use F equals ma. I'm going to do that for each of these 3 objects. I could do 2 equations, 1 for each axis. Okay, so let's go ahead with this. Let's start with okay. We'll start with up here with M1. Okay, so these are going to be the equations for M1. Okay, so we can do 2, 1 for the x-axis, 1 for the y-axis. I of course am going to choose my axes like this, right? X and Y, call up and right positive. Now, going outward. So when I do this, it's going to be, some of the forces in the X is mass times acceleration in the X, right? And so it's going to be just T is equal to, and the system is just M1, so that's the mass, and then acceleration in the X-axis, all right? Now, is anything here accelerating vertically? No. So all my y accelerations are going to be 0. They're all moving together, right? All this is accelerating along together, okay? And so we can say, right, because if I looked at this as one big system, do you realize there'd be this external force shoving and there's no other forces? So this thing has an unbalanced force horizontal. The whole system is going to accelerate. They're all going to have the same horizontal acceleration. So I don't need this subscript anymore. I can just get, it's the only acceleration in the problem. Everything has the same horizontal acceleration. So I'm just going to call that A. All right. Okay. I can do the vertical axis for that guy. I'm going to do that here. All right. Normally I go horizontally. I'm going to do vertically just because I'm going to try to squeeze everything on this page. I know what you're thinking. You're thinking, really, Mr. C? You've got all the paper that you could ever want. Well, ish. Are you really going to do that? Okay. Hey, you say, you know what? The acceleration of the y is 0. So when I do my up and down axis, right, we say I'm going to have just n13 minus m1g equals 0, right? Okay, now let's go to M2. I'm going to do M2 in another color. Look at me, color coding. Let's make M2 green. Sure. Okay, so let's talk about M2. And you're going to say, hey, that's going to be in the horizontal. It's going to be N23 equals M2 times that horizontal acceleration it has. Now, and I can do my vertical axis. and do my sum of the forces in the y is mass times acceleration in the y. But we know the acceleration in the y is 0. And so we're going to say in the y, I've got t minus m2g equals 0. All right. These forces have to balance out because we're not accelerating. We're told that everything is going to remain stationary relative to the cart. So those have to balance out. And I know that you're thinking to yourself, wait a minute. I thought that when you had a pulley, that you would pick like a direction along the string to call positive. So if I call to the right positive here, I got to call down positive there. Sure. Okay. If this was going to be accelerating along, I would want to do that. But in this case, you realize if I call down positive and up negative, it would just be, instead of t minus m2g is 0, it'd be m2g minus t is 0. And you recognize that that's the same equation, right? All right. But more importantly, you say, hey, the reason why we do that is that when we have motion, we say the right for this guy would be the same as down for this guy, right? They'd have the same acceleration, the same velocities, and the same. But in this case, they're not moving along that axis, along that string axis, right? So I don't feel bound to do it that way. I mean, I probably ought to. It's good habit to call one direction along the rope positive. But anyway, no, not going to do it. I'm going to leave it like this. Okay, because I really am just using x and y axes for this problem. I'm not doing it along the string because there's no motion along there, so I don't have to worry about that. Okay, so I am worried about just looking at overall left, right, and up, down. Okay. So here we go. So that's what we get. And then let's go to, just for completeness, I guess I'm going to do this guy. Now, this guy's, okay, sure. So let's do this guy in another color. Let's see here. Sure. Okay, I'm going to make this one this nice rose color. So here is M3, which was big M, but I'm calling it M3. So we do some of the forces in the X is mass times acceleration in the X. And so you say, hey, that's just going to be horizontal forces. Hey, there's just 2 of them here. It's going to be big F. And you're like, oh, good. That's the thing I'm trying to solve for. I'm glad it showed up in an equation at last. Minus N32 equals, again, my system is just that big guy. Okay, so just M3 times acceleration, that horizontal acceleration. Okay, and I can do the vertical axis if I wish. Some of the forces in the y is mass times acceleration in the y, right? But that acceleration in the y is 0. And so I'm going to have going up minus down. So I'll have N3 by the floor, right? Minus normal M3 by 1 minus M3G equals 0. All right. Okay, and there we go. So now I have 6 equations, right? My job is to solve for F in terms of M and G, right? So you're like, okay. Okay, so I'd like to get rid of N32, and I'd like to get rid of A, because I don't know the acceleration, right? How fast it's accelerating sideways, okay? So I want to get rid of A, and I want to get N32, okay? Now, N32 is the same as N23. That's an action-reaction pair, a Newton's third law pair. M3 shows on M2, and M2 shows back on M3. So those are the same. So N32 and N23, these are the same. So I could substitute this in where I see N32. I can substitute M2A, all right? And that will get rid of M32, but I have another A. I still have A. I got to get rid of that acceleration. So you're like, well, I got to come with another equation, right? Something else that has acceleration in it, right? Well, this is the only one with acceleration. But this gives me an equation in terms of M1. That's okay. That's one of the givens. And T, like, oh gosh, I got to get rid of T. So I have another equation with T. Oh, I do here. I can get T in terms of M2 and G. And hey, that's all variables that I know. So I'm going to be actually combining this one, this one, this one, and this one to solve. Is that okay the way I just described that? I hope that's okay. So I'm going to be doing this chain of substitutions that will give me an expression that has F and just all M's and G's, things I know. So running through then. All right. Now, can I get both of these in the frame? It would be swell if I could. I'm not sure. Oh, I can't if I do it this way, right? Okay. I think you can see all those there. All right, so I'm just going to start here. Okay. I'm going to go ahead now. I'm going to work kind of from the end here, substitute this in for t, right? And then substitute that expression in for a, and then substitute that expression n23 in for n32. So I'm going to kind of go around like that, I think. Nah, we'll start with the formula of f I'm trying to get. Okay, so I'm just going to copy this pink one down. F minus n32 equals m3a. And you say, hey, there's two unknowns I got to get rid of. I got to get rid of n32, and I got to get rid of a. So n32, I'm going to say is the same as n23 here. So I'm going to substitute m2a in there. So f minus, and then n23 is m2a, okay, equals m3a. And at this point, you're like, okay, the masses, I know all the masses. I just have one unknown, the acceleration to get rid of. Now, there's not an a in every term, so I can't just divide it out, right? Okay, so I need to go ahead and figure out something to substitute in for a. So I say, well, the only other equation that has a in it is this one. So I'm going to have no choice. I'm going to substitute in, can I rearrange this real quick? You'd say, yeah, rearrange. A is t over m1. Okay, so I'm going to substitute that in here, okay, for a. So I'm going to have t over m1, right? And again, a is t over m1. Okay, so I substitute an equation that has a's for an equation that has t's, and you're like, is that really an improvement? It is, because look, see this guy? We can rewrite t in terms of just m and g, which is what we need. So I'm going to rewrite t in terms of mg. T will just be m2g. So I will get t minus m2 over m1. And then where it said t, I'm going to substitute in m2g. Okay, yes, that's an m2 times an m2. It'll be an m2 squared. On the other side here, I've got m3, and then over m1, it's a t over m1 where it says t. I'm going to substitute in m2g. So now I have an equation where I have f, and the rest is all givens. I'm going to slide this to the other side, and what I will end up with is, add this over there, I'm going to have m2, m3 over m1g. That's this term. Then this term adds on, plus m2 squared g over m1. Now, it's common on like, we could make this a little bit prettier, okay? If we wanted to, see how they've got a common denominator, and they both have g on top, and they both have one m2 on top. So I can make this like g m2 over m1 times the quantity, right? m3 plus m2. Okay, and that's like the tidiest form that I can get this in. Okay, and that's it. Okay, and we were given the three m's, and g is a universal constant, so that's it. That is our expression for f. Yep, you'll notice that this is adding a mass to a mass. This is going to give me kilograms. I'm going to cancel out a kilograms on the bottom here, but then I still have another kilograms, and this is in meters per second squared, so I'm going to get kilogram meters per second squared, which is the unit for newtons, right? That's what Newton is. So that's all good. Okay, that's it. Okay, so this is how hard you have to shove in order to get those blocks to not move, okay? Because this whole thing is accelerating to the right together, and just as fast as this thing wants to accelerate to the right because of this weight pulling on it, that is how fast the whole cart is accelerating to the right. So they end up accelerating together. Do you see that? And that's why this never falls. Neat, neat, neat.